Hello, welcome to my talk for the SPIE Security and Defense 2020 on the track for the millimeter wave and terahertz sensors and technology. I obtained my PhD from Cambridge, and I'm currently a research fellow from Imperial College and the University of Southampton. Today, I will present my research into millimeter wave beam steering with analog resolution and minimized distortion based on liquid crystals tunable delay lines with enhanced signal-to-noise ratios. The agenda will begin with an introduction of my motivation to do this research based on the understanding of the current status in millimeter wave beam steering, in particular the technological gap that needs to be addressed. Let's begin with some research background. Arguably, the availability of 60 to 90 GHz spectrum is promising in a response to the rising demand for bandwidth. Historically, large electrically steered radars were deployed for mixed-site tracking, guidance, and fire control. But in addition to the military sector, phased array antennas also exhibit a huge commercial potential in 5G wireless communications, as well as satellite communications, navigation at 60 GHz, intelligent transport at 63 to 64 GHz, and 77 GHz automotive radar for adaptive cruise control, and 79 GHz monopath short-range radars for vehicle collisions avoidance and traffic monitoring. The conventional beam steering by parabolic reflector satellite dishes are based on mechanically rotating the antenna. The top right figure here shows a radar dish decommissioned for air traffic control at the London Heathrow Airport. These large, bulky, mechanically controlled parts are vulnerable to inertia and vibration, resulting in poor reliability and huge maintenance costs. Instead, there is an increasing demand for the electronic beam steering by phased array antennas like the one shown on the bottom right, a static antenna array solution. Adapted array smart antennas can allow steering the beam to a given direction of focus without any mechanical rotation, but just by changing the excitation phases of each radiating element. Accordingly, phase shifters or tunable delay lines will be the key components in a phased array. There have been a variety of methods to realize the phase modulation in the microwave and millimeter wave regimes. Existing microwave switchable techniques such as MEMS and solid-state PIN diodes offer ultra-fast but resolution-limited phase modulation solution due to this binary nature. Let's have a look at the conventional switching-based delay lines and the mechanism. The phase delay here is tunable by switching between different physical lengths of transmission line or waveguide and producing the corresponding phase shift such as 45, 90, and 180 degrees in the figure here. And due to this limited space for placing the different physical lengths of the transmission lines, the phase delaying of possibilities would be a binary in nature, and a continuous analog phase shifting can be achieved by putting the continuously tunable dielectrics like liquid crystals in a guided structure to change the wave speed and hence the output phase of the transmission line. So pneumatic liquid crystals have been demonstrated with a decent dielectric tunability and low dissipation factor, particularly at millimeter waves. The dielectric tunability is attributed to the molecule shape anisotropy, and therefore the dipole moment variation from perpendicular state to the parallel state, with an applied low-frequency bias field from below the Friedrichs transition voltage to a saturation voltage. The variable polarization allows a continuous tuning of the dielectric constant and therefore a differential phase shift when interacting with a millimeter wave signal propagating over the delay line. With the decrease of the wavelength from microwave to millimeter wave, the device performance is degraded. Less observable at the microwave can be more noticeable in the millimeter wave. And to our knowledge, the high insertion loss at the millimeter wave remains a key challenge for the LC-based planar phase shifter when competing with the waveguide method. In my previous work in tunable delay line phase shifters based on the high anisotropic liquid crystals as the tunable dielectrics, I have pushed the limit of the planar microwave transmission line implementation from the 10 GHz microstrip to 60 GHz enclosed coplanar waveguide and progressively towards a 90 GHz high aspect ratio coplanar waveguide that challenge the current status of the manufacturing in terms of the electrode patterning and the LC alignment. Furthermore, I have pioneered an all optically controlled analog phase shifter at X-band with insertion losses balancing. For the existing liquid crystal enabled reliable delay line technology, the practical resolution is degraded by noises, and more fundamentally, the higher order modes, the surface wave, radiation, impedance mismatch, and amplitude unbalancing challenge these delay lines for the wideband high resolution millimeter wave beam steering. By ways of the illustration, the figure on top right outlines the principle of liquid crystal tuning based on the dielectric anisotropy, producing the dipole moments that align themselves in the direction of the low frequency bias. The classical structure of the two planar electrodes is illustrated, separated by a distance where the liquid crystal and alignment layers are placed. The cell gap is within the range of the anchoring effect enforced by the surface treatment. The figure on the bottom right points out the unequal potential problem occurring at the millimeter wave for the conventional coplanar waveguide structure with the floating electrodes, which limits the operation bandwidth because of this propagation of the multiple undesirable slot line modes, parallel plate mode, and waveguide mode. To address the stray modes and noises, we designed and demonstrated liquid crystal-based ultra-wideband true analog 0 to pi and 0 to 2 pi true time delay phase shifters driven by 0 to 10 volts bias. The delay lines are designed in a stray mode free enclosed coplanar waveguide structure for 1 to 67 GHz. And featuring a semi-shielded enclosure electrically bonding the coplanar grounds. The proposed ECPW layout and the biasing scenarios are shown in the figures here. The main advantage is the enhanced signal-to-noise ratios due to the elimination of the unstable floating electrodes without using the lossy bond wires or the complex vias, and in the meantime allowing the use of the well-established planar PCB and the liquid crystal microwave technology. In addition to novelty of the structure for screening out the noises, a few new approaches are incorporated to enable liquid crystal millimeter wave phase array with enhanced performance, such as the smart impedance matching for balancing the output signal's amplitude and minimizing the beam steering distortion. Two designs of different phase shifting ranges, 0 to pi and 0 to 2 pi, and they are different only in the line length, are fabricated. So the figures here showing the processed substrates of the different sizes before assembled, and as well as the assembled delay line with alignment and filled with the liquid crystal, as well as a whole device of a 0 to pi delay line prototype and packaged with the connectors. The developed liquid crystal-based ECPW delay lines are scoped for integration into the phase array antennas as a non-mechanical millimeter wave beam steerer with lightweight and small footprint. Tilting the main robe of a linear array consisting of equally spaced elements can be realized by controlling the voltage bias to each unit by each pixel excited by a liquid crystal-based ECPW delay line. And with the emitters fed by the proposed high-performance delay lines, a linearly increasing phase progressing profile could be produced and allowing the individual wavefronts to be propagated diverse distances at a given time, and therefore radiating coherently along a desired direction. To unleash the possibility of the insertion loss balancing, we leverage the impact of liquid crystals' dielectric anisotropy on characteristic impedance, and thus tailor the return loss for amplitude compensation without additional amplifiers or attenuators. The method here is implemented by designing the ECPW geometry to perfectly match it 50 ohm at the liquid crystal's largest absorption loss state, which is perpendicular state. And in the meantime, let's match it at the other biasing states, and least match it at the liquid crystal's smallest absorption loss state, which is parallel state. In this way, the increased liquid crystal absorption is cancelled out by a lower return loss, and the reduced liquid crystal absorption is compensated by a higher return loss, and therefore resulting in a largely balanced insertion loss amplitude profile for the minimized steering distortions. And the insertion loss and the differential phase shift performance are measured by the vector network analyzer and plotted against each other at 67 GHz as summarized here. And as can be seen in the figure, the 0 to pi delay line exhibit a maximum insertion loss of minus 4.37 dB at 0 volts bias, which is a 0-degree shift state, and with a variation of the insertion loss in the amplitude only up to 5% for other phase shifting states. So in addition, the 0 to 2 pi delay line exhibits minus 8.28 dB, and the maximum variation level is 8%. Yep, so in conclusion, this work pioneers the liquid crystal-based millimeter wave beam steering technology with 4 main advantages. Firstly is the 0 to 2 pi continuous phase shift for unlimited beam steering resolution. Second is the true time delay nature for the beam squinting free performance. And third, the linear phase shift voltage response. And last but not least, the standalone amplitude balancing solution without additional bulky compensation networks. For more interesting details about optimized scenario for the delay line deployment for beam steering, you can read my SPIE proceeding paper, in which you could find out my novel design for flexible and modular delay line deployment scheme for the beam steering with a smart combination of 0 to pi and 0 to 2 pi delay lines. Thank you for your attention.